Okay, now let's talk about drilling direction and staying in zone. What do I mean by drilling direction? Well, what's the azimuth that the horizontal, the lateral, is drilled? And in this cartoon I introduced, I imply that the well is drilled in the direction of the minimum horizontal stress so that the hydraulic fractures propagate perpendicular to it. And so red, blue, green, and orange indicate individual stages. Multiple hydrofracts are propagating from each stage. That's because we're assuming we're using what's called a plug and perf operation, which I'll describe shortly. And the hydraulic fracturing process using slick water generates this cloud of microseismic events. You can see real data on the left, schematically shown in the middle, and then the representation on the right, which I've mentioned earlier, of these tiny little slip events surrounding the hydraulic fracture. And so some people use the term complexity to describe what's happening in the reservoir. It's not just planar hydraulic fractures. Everybody who uses that term means something different, but is it complex? Well, I guess it is. But to me, the complexity is rather simple. Planar hydraulic fractures, hydraulic fractures that are absolutely perpendicular to the least principal stress as shown, surrounded by this zone of shearing resulting from slip on pre-existing faults in the formation, and of course the microseismic cloud surrounding each hydrofrac is an indication that that's occurring. So the obvious question is, how important is it to drill in the direction of the minimum horizontal stress? And on the left, we see a couple of wells discussed previously in which the lineations of microseismic events, essentially perpendicular to the wells, well path, are in an indication, this is the Eagleford Formation, that those three wells you see there, I'm only showing data for two of the three wells, those three wells were pointed in the direction of the minimum horizontal stress so that the hydraulic fractures propagate perpendicular to their path. The well spacing is designed so that the hydraulic fractures in the stimulated zone from one well sort of abut the hydraulic fractures in simulated zone of the adjacent well. We'll talk about well spacing at a later time. The figure on the right is from the the Duvernay Formation in Canada, and it's a study done by Shell, and they drilled two wells. The direction of maximum horizontal compression is northeast-southwest. So the well that's oriented to the northwest-southeast they refer to that as the on-azimuth well, and the well that's north-south they refer to as the off-azimuth well. 16 stages in one case, 17 stages in another. The stage length is slightly varied, 80 meters in one case and 100 meters in the other. What you can see are the microseismic events, the clouds surrounding the hydraulic fractures, and these are very, very pronounced in the off-azimuth well. You can see the clouds extending in the direction of the maximum horizontal stress as expected. The clouds surround the hydraulic fractures in the on-azimuth well, but they're not nearly as well designed. Now, it turns out that the off-azimuth well was principally hydraulically fractured with slick water, so there was a lot of leak off of the pressure out of the hydraulic fractures and therefore stimulated lots of microseismic events as shown. In the other case, the hydraulic fracturing was done with more of a hybrid fluid, use of gel, a more viscous fluid in general, and you're getting far fewer microseismic events, indicating less pressure leak off. Okay. But as it turns out, the on-azimuth well, the well that is drilled in the northwest-southeast direction, is actually much more productive than the well drilled in the north-south direction. And the authors of this paper, Stevenson et al., argue it's because of the fact that the hydraulic fractures sort of take off in the right direction, right at the well, and propagate out in the right direction in a very straightforward way, whereas in the off-axis well, they sort of take off perpendicular to the well and then have to turn to be in the direction perpendicular to the least principal stress. And they argue that this sort of tortuosity associated with the hydraulic fractures, this sort of tortuosity associated with the bending of the hydraulic fractures near the well, is actually choking off the flow of hydrocarbons back to the well, even though they did a very good job of stimulating slip on lots of pre-existing faults due to the use of slick water. So that's their explanation. It seems plausible, but in fact, the on azimuth well was much more productive, and obviously the lesson they took from that is to drill the wells in this area in the northwest-southeast direction. This is a result for the Bakken well from a study that is now underway. Irfan Rostami is an undergraduate student at Stanford and working with Naomi Bonas and I, and we decided to take a look at the importance of well azimuth in the core area of the Bakken Formation in the Williston Basin. And this is an image from that work. The wells are shown on the left, wells that are east-west and wells that are north-south. Obviously, because of the leaseholds, often being 1 mile square, it's easier if you drill the wells north-south or east-west. You can get more wells on a given leasehold. So that's why they were commonly drilled north, south, and east, west. But the question we were asking is, well, how important is that? And in this area, just coincidentally, the direction of maximum horizontal compression is northeast, southwest. So one would think the northwest, southeast oriented faults are drilled in the proper direction, and the east-west and the north-south faults are in the improper direction. Now, over time, more and more proppant was being used in these frac jobs, and so we used the colors of the well lines to indicate 0 to 200 pounds of proppant per foot. That's the blue line, all the way up to 1,000 pounds or more of proppant per foot. So the blue represents the least amount of fluid in proppant, and the pink color represents the most. And this is also sort of reflecting the epoch in which the wells were drilled. All the operators were sort of steadily increasing the amount of proppant over time. So you can almost think of this as a time plot, with the blue being the oldest wells, the red being the next oldest, green, etc., with the bright pink color representing the most recently drilled wells. Now on the right, we're looking at 24-month oil production in barrels per foot of well. Now most of the wells are about 10,000 feet long, but nonetheless we did normalize by the length of the well. And we're grouping the wells in these 20-degree bins based on their azimuth. So because the maximum horizontal stress is about north 45 east, the minimum horizontal stress is north 45 west in this direction. And so the wells drilled about north 45 west are drilled in the optimal direction, and the wells drilled either east, west, and north, south are drilled presumably in a non-optimal direction. We divided the data up into temporal epochs, and then the blue, red, green, black, and pink represent different periods in time. The numbers, this 50, for example, represents that this average production is from 50 wells. This average is from 2 wells, and therefore is much less significant. Now, what you can clearly see in this data is essentially for all epochs, the wells that are drilled north 45 west are much better than the wells drilled either north-south here or east-west here. In fact, it's about almost a factor of 2. So I think it's really in this subset of data, it's actually irrefutable that in fact drilling in the correct direction is far better. One thing you might note is these pink wells don't follow this pattern and have less production in general than the other wells, and that's because the most recently drilled wells are generally infill wells, so they're affected by previous production. You can see that over here where these recently drilled wells are in the gaps between wells previously drilled. And this data set is looking at very few wells, and so they're not very robust averages. Nonetheless, the big story is drilling on azimuth is much better, on the order of about a factor of 2 better in cumulative production over a 2-year period than just arbitrarily drilling in any direction. And the direction seems to matter more than the amount of proppant. Now, as we think about this issue, we can think about other areas that have been developed extensively. The map on the left shows the portion of the Delaware Basin in the westernmost part of the Permian Basin in West Texas, and then southernmost New Mexico at the top. The black lines indicate the direction of maximum horizontal compression. We've seen that in the stress maps that I presented, the maps prepared by Jens Erik Lundsny and I. And that rotation of the maximum horizontal stress from east-west near the border of New Mexico to a northwest-southeast direction in the southern Delaware. Now, what you can see, the green lines are the well paths. And so you can see up here, the stress is more or less east-west. The wells are drilled more or less north-south, and that's, exactly what should be going on. But in many areas, the wells were drilled in orientations that don't make any sense at all. So, this is okay. But down here, it's highly questionable about whether or not these wells are going to be as productive as they would have been had they actually been drilled in the direction, indicated by the stress field, which we're showing in black on the left. It turns out that the stress field we're looking at is very well supported by the earthquakes, the red dots in the area, and the style of faulting. We're getting a little ahead of ourselves, but we can see that we have northwest trending normal faults with normal faulting focal plane mechanisms. So we know the stress state quite well. Earthquakes occurring in the area are defining for us the faults that are perfectly consistent with this stress state, but the orientation of many of these wells are highly oblique with respect to the stresses, and one must wonder whether or not these wells are going to be as productive as they would have been had they been drilled in the correct orientation. So I've made the point, and I want to emphasize it once again, that hydraulic fractures are always controlled by the magnitude and orientation of the least principal stress, which is usually SH-min. And some remarkable data in support of these sort of theoretical or laboratory simulations have become available in the last few years. One set of data comes from a drill-through, core-through experiment conducted by ConocoPhillips in the Eagleford, and this is from a paper by Kevin Ratterman and his colleagues. Now, P3, this is the well that was being hydraulically fractured, and the yellow is due to a tracer that's indicating fluid, penetrating the perforations along the well. The adjacent wells were often used for were drilled afterward or even cored afterward, and were used to understand how the fractures that were generated in P3 extended away from P3. So below here you can see core, a slab of core, and an FMI image that are showing multiple hydraulic fractures hundreds of feet away from the P3 well. There are far more hydraulic fractures. In fact, there are about 25 times more hydraulic fractures that are seen in the core and seen in these well logs than perforations. So somehow the hydraulic fractures, as they propagate away from the well, are bifurcating, and a single hydraulic fracture, let's say, that starts at a perforation is actually bifurcating into numerous hydraulic fractures in the far field. Now, there's very little proppant in these fractures. How much fluid is in the hydraulic fracturing fluid is unknown. There are a number of questions about exactly how this is occurring, but one thing that's perfectly obvious is that when you map these hydraulic fractures, which is seen through these stereo nets and the Roche diagrams, is that the direction, the azimuth at which these hydraulic fractures are propagating in each of these observation wells are exactly the same, very tightly clustered, and exactly perpendicular to the direction of the least principal stress. The hydraulic fracture is always going to want to propagate perpendicular to the least principal stress. In a moment, we'll see something very similar in the Midland Basin from the HFTS experiment, the hydraulic fracturing test site experiment in the Wolfcamp Shale of the Midland Basin. So here in the Eagle Ford, this direction we see from the ConocoPhillips experiment is exactly consistent with what we would expect from the stress map and is exactly consistent with what was seen elsewhere. This is another operator, another data set, the lineations from the microseismic events. So the scatter that we see, this cloud of events, which I argue some of which may be uncertainty in the locations, but in fact, these events are small earthquakes forming as a result of pressure leak-off out of the hydraulic fractures in a cloud around the hydraulic fractures, but the scatter of these events is not implying non-planar hydraulic fractures. This data argues very strongly that the hydraulic fractures are planar. Now, this simple picture then, shown on the right, which you've seen many times, can be, discussed quantitatively, and we're going to do that when we just discuss chapter 10 in the book. We're going to look at these fractures in a stereo net. We're going to use some very straightforward geomechanical arguments to talk about how these slip on these fractures is stimulated by the high fluid pressure leaking out of the hydraulic fracture. So these Moore diagrams on the far left will be discussed later. But what you can see, is in fact, from the stereo net, is in fact that the planes have a wide range of orientations. Those are the natural fractures. And then the stereo net below, which is from the earthquake focal mechanisms, are very consistent. The orientation of the planes that slip from the focal mechanisms of these microseismic events is basically exactly what one would have predicted from just looking at the images in an image log that was collected before the stimulation process. So my view of complexity is illustrated here. Planar hydraulic fractures surrounded by a cloud of slipping pre-existing faults. But others may not agree, and here are a couple papers from the recent literature in which there are representations of sort of complex fracture patterns that are sort of anastomosing hydraulic fractures, maybe hydraulic fractures intersecting and interacting with pre-existing fractures. The picture on the right, in fact, is even proposing to calculate which elements of that complex network, sort of honeycomb of intersecting fractures, are actually taking proppant of different sizes. I think it's quite imaginative how representative it is. I have my doubts, but nonetheless, when you come right down to it, and what we will show in future lectures, is when you're history matching production. In other words, when you're trying to understand the drop off of production with time from these unconventional reservoirs, which I've already talked about, one cannot really distinguish between these various models of complexity. What is really important is how much area you've created that's in contact with the reservoir at depth, and one can get that area sort of my way through these multiple slipping pre-existing faults, or you can get that area through other representations such as these. And what's really important is how much area is in contact with the matrix. And one cannot distinguish between very different physical models if, in fact, they're all contributing the same amount of area of contact. This is something we'll come to in future lectures. HFTS, the hydraulic fracturing test site, involved a slant core well, which went across some stimulated wells. One well was in this case, the upper Wolfcamp, and one well was in the lower Wolfcamp. You can see the stages indicated by the discs in the upper diagram, and then sort of zooming in on the well in the upper Wolfcamp, one can see a representation of fractures that are in the core. And you see many, many hydraulic fractures in the core. Many more hydraulic fractures are seen in the core than, in fact, the number of perforations, just like in the Eagleford data. And when one plots the orientation of those fractures on a stereo net and Rose diagram, once again, just like the Eagleford, we see they're tightly clustered. They propagate parallel to SH max, perpendicular to SH min, and that's basically what's controlling the orientation of the hydraulic fractures, just like in the Eagleford case. In this case, they also, documented the occurrence of the hydraulic fractures. They traced the amount of evidence for proppant and core, and frac fluid, and it's a very interesting and complete story that has been described by Julia Gale and her colleagues in the ERTEC paper that's indicated, and a number of other papers have been written as well, distinguishing the hydraulic fractures from the pre-existing fractures, documenting when proppant and evidence for drilling fluid is found. Now, we use logging while drilling during directional drilling to tell us, when we are in the formation that we want to be in and when we drift out of it. And on the left is a list of different kinds of geophysical measurements. The easiest to make is a gamma ray measurement, and often these formations will be characterized by different degrees of gamma radiation. So therefore, it's a simple and convenient way of making a measurement while drilling in order to stay in zone. However, there are many other types of geophysical measurements that can be made, and the more information you have, of course, the more you're learning about the formations. And if you do those while drilling, the more you're able to stay in zone and guide the well appropriately. And here's, two examples I've, briefly referred to before. The upper example is a well trajectory with microseismic data from the Marcellus Formation in West Virginia. And one can see that, in fact, two distinct formations were encountered. The one shown in gray, which is the Cherry Valley limestone. The number, the well sort of started in that, and then they deviated the well down into the lower Marcellus, as shown by the light green, and carried out a number of stages. This was particularly important because the stages in the lower Marcellus, tend to be horizontal, the hydraulic fractures from those stages, whereas those in the Cherry Valley seem to be vertical. The lower case is from the Woodford Formation in Oklahoma, and you can see there that they wanted to stay in that middle formation, which was optimal. The log that's shown there in this cross section is gamma ray, but down here they're using actually spectral gamma, and they're showing the total clay plus kerogen content. But the important thing here is, they drifted out of this Woodford 2, the middle formation, and then they steered back in to the well where they wanted to be. They back into the middle formation, and then they drifted out again, and they steered back in and drifted out. And so the problem here is this is only about 20 feet thick, and the sensor, the gamma sensor, is about 80 or 90 feet behind the drill bit. And so they're already, when they were here, by the time they know they're out, they're really out, and then they bring the well back. And so while the capability to steer and stay in narrow zones is really quite remarkable, having the information available to tell you when to steer and when the trajectory has to be changed is really quite a challenging feat in many cases. In the upper case, they seem to have drilled most of the well in the lower Marcellus where they wanted, although the initial landing zone turned out to be above the lower Marcellus, and then they had to deviate down into it, and then they stayed in it. In the lower case, they were sort of fighting the well being in the correct lithophases, and the variation of the physical properties of these three sections of the Woodford are fairly significant, and so you pay a real penalty when you drift out of the well. And if you sort of think about the information available to you, if you're just looking at, say, clay plus kerogen, you're kind of interested in that, seems logical. The organic content is varying. In the lower diagram, it appears to be varying along the length of the well, but in fact, it's varying because the well is porpoising in and out of between two different zones, one of lower clay plus kerogen and one with more. So there's a lot of speculation about horizontal variability in some of these formations that is really the result of stratigraphy, but you're sampling it through a well that's porpoising between different stratigraphic layers. And so what is really just simple vertical layering is misinterpreted as lateral variations. And, we've seen an example like that. And of course, this example we've seen before, this, very clay-rich zone at the top of the lower Eagleford, which of course is not very brittle, produced very few microseismic events, and was not producing very much gas. So well steering, of course, is not only trying to put you in the best formation, but is also trying to avoid the poorest formations to be doing hydraulic fracturing. And, this is a blow-up of showing a couple of wells. The well on the left is called a toe-up well for obvious reasons. The well on the right is, called toe-down, and there's about, 49 stages in the well on the left, 47 stages in the well on the right. They're pretty much staying in the zone they wanted to. And this issue of toe-up versus toe-down is something which is determinable, achievable, but you've got to sort of know you want to do it. Now, as shown, the wells are toe up and toe down because the formations are dipping. And so that sort of defines the orientation of the well. It's going toe down because it wants to stay in the right lithophases. It's going toe up in the case on the left because they want to stay in the right lithophases. But this is, in many cases, this is an option, and operators have to decide in a given area should they preferentially drill their wells toe up or toe down. And if you think about it, if you're producing Water, for example, the water may be ponding up near the heel of the well in the case on the left, and potentially could even block flow of the hydrocarbons from later on. In the case on the right, the water would be ponding up near the toe of the well, and maybe that's not as bad. However, the well on the left would be easier to, if you wanted to go in and just blow out the water, it'd be easier to get it out in the well on the left than it would be on the well on the right. So this issue of toe up versus toe down is something that companies experiment with and then make a decision based on geologic factors or reservoir factors.